Hello everyone, I'm Sriram Murali and today I'm here to talk about Carruthers theory. So first, to give a quick example, before I actually go into the details about polymers, I want to give you an example of, imagine you have a supply of paper clips, and I told you your goal is to make a chain that's as long as possible. In this case, the length would be 4 paper clips long. Now in an ideal world, you would say this is really easy. The length of the chain would just be the number of paper clips I'd given you. And while that's true, it's not that easy to make a chain that's completely linear like this. In a real world, you could imagine that if I tried to tangle all the paper clips randomly, it would come out looking something like this, where it's not a single chain and instead there's a lot of branches, as shown here, or multiple different smaller chains. And now these chains are a little bit confusing, and if we wanted to quantify them numerically, there's a couple of things we could do. First would be xn, which is the degree of polymerization, and this basically answers the question, what is the average number of paper clips per chain? So for above, we have 8 paper clips in this first chain, 3 in the second, and 4 in the third. So this would be 8 plus 3 plus 4 divided by the number of chains, which is 3. So in total, we get 15 over 3, which is 5. So this degree of polymerization is 5. However, if we had a fully linear chain, it just would have been the number of paper clips, which is 15. Another quantity we use to quantify these reactions is P, which is the extent of reaction. This basically answers the question, how much has the reaction progressed? So to calculate P, you use the number of paper clips initially minus the number of chains or paper clips remaining at time t divided by the number of paper clips initially. So here we originally had 15 paper clips, and at the end we have 3 more chains and 0 paper clips just left lying around. So we do 15 minus 3 over 15, and we get 80%. Now you can see that as we get closer and closer to a fully linear chain, basically as this number decreases and these two stay the same, we would get closer and closer to 100%. So this is kind of what Carruthers theory quantifies, the relationship between the degree of polymerization and the extent of reaction. So it says that xn, the degree of polymerization, equals to 1 over 1 minus p, which is the extent of reaction. So here we can see that as xn increases, p approaches 100%. And that kind of makes sense given our example, where here we had a p of 80%, so 1 over 1 minus 80% gives us 1 over 1/5, which is 5, which was our degree of reaction. But if we increase this p to, let's say, 95%, we would get 1 over 1 minus 19 over 20, which gives us 20 for our degree of polymerization. So as p increases, or it gets closer to 1, we get an xn that's much, much larger. Now moving on to actual polymers. We can think of each paper clip in this example like a monomer, which is a single repeat unit of a polymer, and each chain like a polymer chain. All the same things that we discussed in the example before still happen. Now the equation that we discussed before is actually for a special case of Carruthers theory. That's where we have 2 monomers of equal concentration. You can think of this as having an equal number of red and blue paper clips, and these are reacting. In this case, we have the equation xn equals 1 over 1 minus p, but you can imagine that it's not always going to be the case that you have 2 monomers with exactly the same concentration. There's also a case of different concentrations. Here, we can define a parameter r, which is less than 1, such that r equals the concentration of the monomer A over the concentration of the monomer B. And just for simplicity's sake, we always set the numerator of r to be the one with less concentration. So for example, if we had 8 red and 2 blue paper clips, we would set r to be 2 over 8, which gives us 1/4. And using this parameter, we now have a new equation relating xn and p, and this would be xn equals 1 plus r over 1 plus r minus 2rp. So one interesting thing about this case is that if we set r equals to 1, we would get 1 plus 1 over 1 plus 1 minus 2p, or 2 over 2 minus 2p, which equals to 1 over 1 minus p. And this is actually the equation we had before, which makes sense because r is only 1 in the case where the concentrations of each monomer are equal. So the case we had before is actually an edge case of this more general equation, which is Carruthers theory. Thank you.